Very good. Thank you. Welcome. Thank you. Yes, my name is Mike Long, and I want to talk to you about DevOps and why I believe it ushers in a new paradigm in the world of software and what we should do about it. This talk is largely influenced by this book, The Structure of Scientific Revolutions. It was groundbreaking work created by Thomas Kuhn in the late 60s, and in it he describes the way science actually develops and how that is different from the way we think science develops over history. So for Kuhn, to understand scientific development, we first have to understand the context in which scientists do their work. And I think that there's a lot of transfer from these ideas into the world of software development, and that's what I want to share with you today. So the way we're taught in schools and our textbooks, the way science works is scientists come up with ideas that they want to test. They form hypotheses, and they make them a testable hypothesis. They do experiments and gather data, and the idea is that they're trying to falsify their hypothesis. And step by step, incrementally, we get better and closer to the reality of the world around us. What Kuhn found was actually something very different than this. He found that actually the way science progresses is you have long periods of normal science, and then a revolution occurs, and then everything that people used to believe is thrown out, and now there's a new world. And these worlds, or worldviews, he calls paradigms. So it's actually from Kuhn that we get this kind of overused phrase, the paradigm shift. So what he found was that there's a cycle in the way science progresses, and it starts with normal science, which is kind of similar to the way the textbooks describe things. This is kind of normal. We do our experiments. Scientists largely get what they think they're going to get. And their only objective is to try and figure out how to bring the theories they have closer into agreement with the real world. An important thing about normal science is that when you're operating in this world of normal science, you're able to take the foundations of your field for granted. So, for instance, you have textbooks, you have curriculum, you have courses in schools. The foundations of the field are kind of accepted. It's not something people argue about anymore. Where the research is happening is on refinement in the research areas. So this is kind of the Popper ideal, where people are working to falsify their hypotheses. The trouble is that over longer periods, unresolved anomalies accumulate. So some things that don't fit within the paradigm, some things that don't make sense, they're just kind of noise. They don't make sense in your worldview. And some people start to question, is this really the right part? Is this the right? Do we have the right theories here? Is the foundation correct? And the thing is that we will still continue with this idea of science unless there's something better to replace it with. At some point, the anomalies accumulate to such a degree that we enter a period of crisis. And during this period of crisis, people are understanding that there's no more ways to account for all these anomalies. We can't keep adding little bits and pieces to the foundations of our field that don't really fit into the theories. And people try all kinds of different things. People start to question the textbooks that they're basing their field on. The only way to get out of a crisis is to have a revolution, and this is what he talks about in terms of scientific revolution. This is the crisis can only be resolved by a theory. So now we have the old paradigm and the new paradigm, and the old paradigm has to go. That's the whole point of the revolution. It's just like in the real world. When you have a revolution, the old world is replaced and no longer has any power in. So we have this paradigm change, and it follows the Highlander pattern. There can only be one paradigm. Physics can only operate in one paradigm. Cell biology can only happen in one paradigm. It's impossible to have these two theories. And that's where in the 20th century we had a lot of contention between string theorists and so on in physics. So this is the cycle that Kuhn described. This is how he saw science progressing. Basically, science goes from paradigm to paradigm with revolutions in the middle because it's not really an incremental process towards where we're going. So for an example of this is, there was a time when we thought we were the center of the universe. Some of us still believe that. Yeah, so I mean, it's a natural thing to believe. I mean, we're here, stationary, and everything is going around as the sun goes past, the moon goes past, the planets go past. So it made sense. Since Ptolemy's time, this was like our model of the universe. But then Copernicus came along and said, wow, what about if we were just a planet too, and the sun was really in the middle? That kind of would help to explain all these weird things we're seeing in the sky, right? And Kepler did a bunch of, used again, Galileo's telescopes and gathered lots and lots of data to chart the movement of these planets to see whether that fitted in with the solar heliocentric paradigm. And it turned out to be quite true. So in that period, there was this revolution went from geocentrism to heliocentrism. And then about 50 years later, Isaac Newton realized that, wait a minute, what about if the way a cannonball behaves on Earth is the same as the way the moon behaves in the sky? What about if we could unify terrestrial and classical mechanics? So he came up with the universal law of gravity, and this was actually one of the first universal laws in science. So again, another revolution occurs. Zoom forward a bit, and Isaac Newton was a very, very clever man. I mean, he was a genius. But he did make one pretty big mistake. He believed in absolute space and time. And it was Albert Einstein who came along and said, well, how about if the speed of light was absolute? There's no way to change the speed of light. But time's flow was variable. And it could be affected by speed and gravity. Okay, so that's the history lesson. That's what scientific revolutions are. How does this fit into the world of software? Well, our profession is relatively young, so we don't have a long history of data to go back on. I mean, you could go back to Ada Lovelace and Babbage's machines, but they were computational machines. The first software really came with a Turing machine, where we had some universal way of executing instructions. That was in 1938. Zoom forward only 30 years, and already our profession was in a crisis. Edgar Dijkstra, at the NATO Software Engineering Conference, was talking about how hard it was to make software these days. It was the biggest problem in their field. When we had no software, software wasn't a problem. When we had some software, we could manage. Now we've got lots of software, and it's impossible. And that was a long time ago. But actually, they had a solution to this. And what they realized is that, I mean, they were at the NATO Software Engineering Conference. What they realized was that they were going to engineer their way out of this crisis. What we needed was a new paradigm, an understanding that software is something we need to engineer. We need to do like people building bridges. We need to plan well. We need to figure out exactly what we need to build before we get started. We need to have good construction methods. We need to use data hiding and structured programming, and later we had object-oriented programming. And if we construct things right and we plan it really well, then we're going to get our bridge. And actually, this paradigm served us well for about 30 years. There was a lot of software made between 68 and 98 that was very, very groundbreaking and moved our field forward. But then there were anomalies too. The anomalies started to accrue. Big projects were failing. Very, very big projects. Billions of dollars were being wasted. Sometimes these failures were complete failures, permanent failures. They never got to deliver any value to whoever was paying for the project. There was a lot of discontent as well. But still, these anomalies, these failures were kind of explained away. It was always the project's fault, right? It was either they were not good enough at requirements, or they made the wrong technology choices. How could they pick COBOL in 1989? That's crazy. They should be using C++. Or maybe staffing failures. They had the wrong people, or the people were the wrong gender, or from the wrong country, or they had bad leadership. The leaders didn't know what they were building. They were just signing checks. So there was a lot of anomalies, but people were explaining them away as if that wasn't part of the paradigm. The paradigm was sound. Engineering is sound, but there are just some people that can't make software. There was other kinds of anomalies too. There was positive anomalies. There was people not using the bridge building techniques to make software, and they were very successful at it. Open source software became extremely successful without any of this central planning, control, requirements, management, any of these things. And we started to see new patterns emerge, like use the internet to allow us to scale software development in open source to much broader groups of people, and new methods were coming along, like extreme programming, that were succeeding. But still they were anomalies. But eventually, all this discontent came to a head. And some very smart people started to think of different answers to this question: how do we make software? Maybe we're not making bridges. Maybe we were a manufacturing line. Maybe we were operating in a factory line and our only purpose was to deliver some pieces of increments of value to the customers off our factory floor. I mean, it's a little bit less prestigious, right, to be working on an assembly line than being a civil engineer. But so there was a lot of resistance to this new idea. But eventually, this crisis was resolved again. The only way you can resolve a crisis was with a theory. So there was a lot of people who were interested in these new ways of making software, got together and came up with a manifesto. And they didn't agree on a lot of things. In fact, they spent most of their time prior to this manifesto arguing. That was how they knew each other. But when they got together, they realized there was some things that they did kind of agree on. So they came up with this manifesto and they said, okay, maybe there's another way to make software that doesn't involve us doing blueprints and plans and engineering our way out. And the very first principle of this manifesto, I think, is really, really important. It's the highest priority of any software organization is to deliver value to the customer. And that should be delivered early and continuously. So now we have a working theory for a revolution. Now we can get to work, right? But that's not enough. A revolution isn't enough. You don't get a revolution just from having theory. Anyone can come up with a theory. Theory has no weight. What you need is some achievements. And these achievements have to be sufficiently unprecedented. They have to be something that's never been seen before to make people wake up and pay attention. And they have to be sufficiently open-ended so that there's so many problems left behind that lots of really smart people are attracted to problems, right? We all are. We just want to get the problem. So you need to have you don't want to have the full answers to get a revolution. If the answer is 42, then you're not going to get anyone following you. So there we had it. We already had our history lesson this morning, but there was some important steps along this journey, and that was where we started to get, some achievements on the board. Flickr was able to deploy 10 times a day. DevOpsDays brought together a movement and the community, and then we got our Bible, the Phoenix Project, showed us how these things actually worked. So these achievements were really important steps on that progress. Okay, so now we're into the revolution. We've got some achievements up on the board. People are interested. We're having conferences about it. What next? Well, there's an important role for tools in scientific revolutions. This is true for the law of gravity. It would not have been possible had Kepler not created a bunch of data, and Kepler would not have created a bunch of data if he had not access to the telescope. And the same is true for cell theory. It wouldn't have happened without Zeiss making a very, very good microscope that they could see things with, and then going back through to micrographia, and again back to Galileo, to his compound microscope. René Laennec invented the stethoscope, and then he gathered lots and lots of data about the different sounds people make before they died. And then he cut them open to see what that sound was. But that was really important data gathering, because that gave us a new world of medicine. Because prior to the stethoscope, the only way we had of knowing what was wrong with someone after they died was waiting until they died and cut them open. Now we could start to diagnose things beforehand. And the stethoscope was really important on that process. Again, we wouldn't have the theory of evolution. I know maybe not everyone believes in it, but it's true, okay? It's true. Without the theory of evolution, you couldn't have had that without the Beagle expedition, which Darwin was on. And the Beagle expedition could never have happened if we hadn't got really good at doing ocean voyages. Sometimes it works the other way around. It doesn't always go tool, data, theory. Sometimes it goes theory, tool, data. And that's okay, but you need all three, right? The Higgs mechanism was first identified in 1964. It was postulated. People thought it's probably there because that would explain what we're seeing. But it was a long time later, it was half a century later, where we built a massive tool to go and find it and do lots of experiments and gather data before we could actually confirm the theory. So there we have it. Tools and data are required to sustain theory. This is what normal science is all about. And we have a problem, though, in our field, because we have this idea that agile improves business outcomes. Right? That's the theory. This is what the whole Agile Manifesto is. This is a better way to make software. It reduces risk. It will create better outcomes. The problem is the tools and the data weren't really there at that point. So this is where we get into our normal science phase in software. This is where we start to just do the work. It's less glamorous than coming up with new theories and reinventing the world, but this is a very important part of how progress works. So what we realized was that if we're going to get anywhere, we need a bunch of tools. We need to be able to define our world as code, and we need to get everyone in the team all together in the same place so that we can work together on this stuff to deliver value. We need to get rid of the silos and the handovers and the queues and the rework. Very important. And then we want to say, okay, if our organization is just a factory floor, what does our factory floor look like? Where is our manual processes? Where is our wait states? What is the automation? What is our ability to deliver? All we want to do is to go from a customer need to being able to deliver to the customer what they want. That's the only reason why we exist. That's why software organizations exist. But we're not there. We can't get there without a bunch of tools and technologies. The good news is, as a field, software engineering, software developers, IT professionals, we're really, really good at making tools. In fact, we'd often rather make tools than do customer software, right? But we shape our tools, thereafter they shape us. So all of these tools, I mean, if I was to put all the tools that were possibly defined as DevOps, I would need many, many more slides, but all of these tools were created post Agile Manifesto. And I believe, let's have a show of hands, how many people is working with at least one of these technologies today? Right, so we had the manifesto, and now we just off to the races. We're going to solve this problem. We know the direction to go in. We just need the tools and the techniques, and we need to get together and talk about it. So we've got the tools, but do we have the data? Well, there's some interesting first steps on this. The DevOps Research and Assessment Organization, they've been surveying IT professionals since 2014, I believe. Thousands of them every year to figure out, asking good, solid questions, scientifically rigorous questions about how they make their software and how that affects business outcomes. And I encourage you all to read this report. It's very, very useful. One of my favorite figures in the report is this. This is kind of messy, but what it does is, from looking at the data, they can establish cause and effect. Let's tidy this up a bit. This is kind of the simpler version of the same diagram. So, again, we're only kind of caring about the financial outcomes because that's the thing that keeps us in a job. This is how we make sure we keep getting our salary every month. And what they found was that there is a causal link between having lean product management approaches and continuous delivery to financial outcomes. There is a link that proves this. And you need a bunch of practices and tools to be able to do continuous delivery. And of course, nothing works unless the leadership is behind. But this very simple model there is good data to support this. It's not just some 15 guys in Snowbird deciding to write a manifesto. There's some good data behind this now. And you can gather some data yourselves. I mean, you don't need an awful lot of data to figure out how long it takes you to get stuff to the customer. I mean, these are 4 very simple metrics you can add to your development process. You can probably fit this around the tools you have, Jenkins or whatever, and just get a rough number on where you are in this world. How long does it take you to get from the need to it being delivered? This is a very, very important metric for your organization. Your organization is probably a bit messier than that, though. So you want to get everyone in a room and do it on a whiteboard. Okay, so that's it. I believe we're in this world of normal science. But this new paradigm is relatively fresh. So how do we adapt to this new paradigm? We're not the first industry organizations to have to adapt to new paradigms. Andy Grove has this fantastic book, really fantastic book. And he was the CEO of Intel, and he took Intel from, he led Intel from being primarily memory business to being primarily a microprocessor company. Because he saw the writing on the wall. There was more and more competition in the memory business. It was driving the prices down. The market was being flooded with memory. And so their margins and their volume were going down. They had a tiny business in microprocessors, but it had a huge potential. The thing is, he had to change his whole organization from one type of business to another type of business, and it's not an easy thing to do. And what he coined this term, the strategic inflection point, for this point at which you adjust to the new world, accept the new world, and jump on and attack that new world, and to ignoring this new world and watching your business decline. And we've seen this with Kodak. They were not able to move from agile to digital photography. And we've seen it on the other side with Netflix as well, where they've managed to go from shipping DVDs in the post to streaming services. It happens in both ways. The good news is a lot of people are already there. You know, they've already made it. They've made a lot of progress. The future is already here. There's a lot of companies already quite ahead in this curve. And the good news about that is that you can learn from them. You don't have to make all the painful learning mistakes yourselves. You can find out what works and what doesn't. So you probably don't want to be the first person to adopt any new technology. I mean, new things don't work. It's just how it is, unfortunately. But you don't want to be the last either. So you want to find yourself in the right position and take the right risk for the right things. So if you have areas of your business where you're doing this is your core business, the most important thing, you probably don't want to be very aggressive on innovation there until you've got a taste of the flavor. So you probably want to try new techniques and technologies around the fridges. And once you learn and get the organizational capabilities with them, then attack your core businesses. Okay, that's what I wanted to share with you. I believe that DevOps defines the paradigm we are currently in. Because I believe there is a state of consensus. I believe that, in general, there is a consensus that Agile is a theory that works for us, it is serving us, and that DevOps is a practice or a set of practices and principles that is serving us. I don't hear many people saying we want to go back to structured systems analysis and design these days. So I'm very, very confident on this. And I'm also confident that we're into this new paradigm now. Like the crisis is past us, the revolution is past us in a lot of respects. But we need to do the work. We need to make the tools and gather the data and prove our hypothesis to make the next steps forward in our industry. And yes, I believe it does represent a strategic inflection point. There will be winners, there will be losers, and that's the evolution of the world, I'm afraid. So, science, it really works. Thanks for taking the time to listen to me, and enjoy the rest of the conference. Yes, I don't know, do we want QA? I'll be here all day and all tomorrow, so just grab me and I'd love to talk. I'll be at the party. Buy me a beer. Thanks.